Am I audible? Am I audible? Okay. So today we have planned for two demo sessions, uh, similar to the content that you saw in the week's lecture. And first demo will be mostly about the basics of Pytorch, and I try to create and both the demos are in fact you can run those in colab notebooks. And I've tried to create the demos in such a way that they cover most of the content except for the last video, which is about catalysts. So the content of that video already provides code with it, so you can go through that code, and if required I can just show you how to get that code. And for the rest of the 5 videos that are present in the week's content, I have tried to incorporate the 2 demos in such a way that they will cover most of that content. We'll wait for 2 minutes and someone else is joining the meet. Okay. So yeah, we'll start at around 6:05. Then I'm just right over. guess we can start. So basically, I have noted down the parts that are present in both of the demos. So the first demo will mainly talk about the basics of Pytorch, and the second demo is about an implementation of a convolutional autoencoder network for a simple task of image denoising. And in the first demo, we'll mostly look at how you can use GPUs in the Pytorch code. We'll also see about the autograd functionality of Pytorch, and we'll look at some operations on tensors. And I will also share the link to the colab notebooks for this. In the second demo, we'll look at how we can create a convolutional autoencoder network with just a few simple lines of code in Pytorch. Then we'll look at the implementation of data loaders, which is very important for. Is this available in YouTube? Yeah, the lecture after the recording, the lecture. Yeah, okay. After the lecture, I will upload the video to YouTube. Most of this content is, somewhere you will find it on YouTube as well. Yes. Am I not audible? Intermittent voice break. Oh. Is that for everyone? Can someone let me know? Okay. Okay. So in the second demo, we'll also look at how you can run a profiler. Okay. Others are having voice breaking. Okay, please let me. If you are not able to hear at any point, you can just put the question in chat and I will repeat the content. Okay. So we'll look at the profiler as well as we'll look at how we can visualize stuff in Tensorboard. So that is the main content of today's session. And I'll first start with the Pytorch basics demo. Before that, would someone like to volunteer so that in case by show of hands, can everyone let me know whether you are familiar with how to run colab notebooks? If not, maybe someone can just volunteer so that we can. Okay. Okay. Would you like to volunteer? Just share your screen for some time, and we'll show how you guys can access the code that I am going to share in your drive. I'll stop sharing for some time so that this stays in the recording. can you share your screen so that would someone like to volunteer? To just share screen for some time and I will take over later. Okay, thank you. So if you go to the link in the chat that I have shared, maybe I will reshare the link. So yeah, you should see the collab notebook as such, and what I would like you guys to do is click on the copy to drive. Yes, and this will create a copy of this notebook. Right now for you guys, this notebook will be in a read-only version. But when you make a copy of this, it will be available in your drive and you can access the notebook anytime. So this notebook you can run freely and edit as the way you would like. Okay, so yeah, that's it. This is just for the recording in case someone else watches and doesn't know how to access the notebooks in their drive. So thank you, Sangeeta. You can stop sharing the screen. I hope everyone is now clear how they can access the code. So at the top, when you are running this notebook, you must be seeing here the option must be there. There will be option for change runtime type. Okay, if you click on it, you will have this option of CPU and GPU, and I want you to select this GPU option and select save. If you should be able to then access the GPU version of this collab notebook, and this I'm seeing on the notebook that you have made a copy in your drive. Okay, so for me actually I have used the collab facility too much today, so I'm not able to access their hosted runtimes, but I'm accessing the code on my local system right now. But it should be similar. The content should be similar for what you see. Okay, so when you can just go through these codes, since that they will now be available in your drive as well. But I will briefly go over the main contents, and later if you want you can make some changes to it and experiment with the stuff. So first we will just import the torch library, and on the TensorFlow, on the hosted collab notebooks, you should be able to directly do this because the hosted servers, they already have this most of the libraries are pre-installed in. And then you can check whether the GPU is available for you. So in case you have selected the correct runtime, you should see CUDA available as true. And if you are not able to see, then make sure that you change the runtime type and do it up, get this output. Okay. And you can also check the specifications of this system that you have access to. So currently I have connected it to my local runtime. So this is different from what you must be seeing. You must be seeing the specifications of the hosted runtime. So the T4 GPU, that is what you will see here, and its corresponding memory. Okay. I hope everyone is able to get till this point. Next, we will look at some basic functionalities. So here you have some a tensor which is being created of dimensions 5, 3. So it has 5 rows and 3 columns, if you imagine 2D tensor. So X is that tensor, and it is having all elements as zeros. Okay, so that is what we are printing here, and the X tensor, and this is what you should also be able to see. Okay, so X is a tensor of 5 rows and 3 columns. Then we are just printing the size of X using this X dot size. Then we are checking if it's actually a tensor by using this X dot type, and we are also checking on which device this tensor is stored right now. So by default, a tensor will not go to GPU itself directly. It will first be present in CPU memory only. So we are just checking what is the device on which it is stored right now, and it should print CPU. Okay. But tensor as an data structure, it can be stored in both CPU and GPU memory. So you will, if you create a new copy of this basically, but which is stored in the GPU. So here at the top we set, if the GPU is available, set the device to the CUDA GPU, CUDA device, so which is the GPU that we are looking. So X1, this variable is now stored in GPU. Right? So we are checking the device of both X and X1 here. So as you can see, device on which X is stored is CPU, but the device on which this X1 is stored is CUDA 0, which means the first GPU that you have access to. Up till this point, I hope everyone is able to follow. You can let me know at any point if you have any doubts. Moving on, we have a simple functionality of creating random numbers. What is toDevice meant for? Yeah, so this is the function that is actually transferring the data from X, and this X1 is a new variable which is now stored in GPU memory. So it's transferring the data stored in X into the GPU memory. That is what this function is for. Okay. Yeah. So moving on, we have two basic functions available in the Torch library, which are rand and randn. So here we are just randomly sampling. These are for random sampling. So often to do some code testing, you can use these functions for some just random test cases. And I'm creating two tensors, x1 and x2. For x1 tensor, I'm doing a random sampling from a uniform distribution, which means every number from 0 to 1 that you will see being sampled in this x1. So I'm sampling basically 100,000 numbers, and of all of those numbers are sampled from a uniform distribution, which means all of them from 0 to 1 are equally likely. We have one more question. If you want to run any code from CPU to GPU, we need to use device command. Is it? Yes. So mostly you don't run the entire code in GPU at once, because GPU memory is also limited. So what you will mostly do in a code is whatever, let's say the task that you want to parallelize, the computation that you want to parallelize, the data for those computations itself you will transfer to GPU memory. So for example, in a neural network model, you want the content of the network, the weights of the network and the model itself, you want that to be transported to GPU memory. So you will transfer your model to GPU, as well as at a certain epoch or at a certain instance of the training, the data that you have at that instance, that also you will transfer to GPU, so that the model can use that data and produce this output, and all of this data will be present in the GPU memory. For the next instance, again that data will be overwritten and the memory will be reused, and so on the process will keep on going. Okay. I hope that answers the question. So here we have, instead of transferring to GPU, why not we have our program and data in GPU itself, as we are now going to transfer data from laptop to server. So yeah, actually we'll come to this point of transferring data to GPU and program. So okay, this what we are doing right now is in Google Drive, but the code that you are running is not running on is basically running on a server provided by Google right now somewhere, and that has it's similar to what you saw in the previous weeks. So the content, the code itself is stored in your Google Drive, but the running of the code is right now still happening in Google's servers. So in a sense, the code has been transferred to their sys server. About the question that you are asking, that why don't we just transfer the entire program and the data to GPU memory, we will come to that in a bit. But in short, the answer to that is GPU memory is actually very limited. You can't transfer the entire data. So often when you are doing machine learning tasks, the data that you will be working on will be in orders of some GBs and TBs. It might depend upon the application, and your GPU memory might not be enough to store all of this data, because the most of the GPU memory will also be used for, let's say, storing your model weights, and basically at a time you will load a batch of data, and only that will be sent to the GPU. You won't send the entire of your data to GPU, because that memory will be limited. Compared to that, you will often have CPU memory far more. Yes, the data itself is in much volume, but the code is not that high. But the thing is, there are some operations which you want to, let's say, run serially in your code, which need not even be present on, let's say, the GPU memory. So that is a not necessary for those part of the codes to be present in the GPU memory. So you basically let them be in the CPU memory, so that you can utilize the available GPU memory as best as you can. So not all computations are good to be done in GPU memory. Some are better to be done in CPU. Yeah. The YouTube video link of this will be shared. So here x1 and x2 are our two tensors. One I am sampling from a uniform distribution and another I am sampling from a normal distribution. So I have 100,000 elements in each of these tensors. Okay, and if you run this, you should see that the size of x is 100,000 elements, and it's a single dimensional tensor. Just to visualize how the the sampled numbers are looking like. So I'm plotting a histogram of the data that I have. So x1 and I'm basically, I'll show the histogram first. So if you run it, you should see that from 0 to 1 I have about 100 bins. So the distance from 0 to 1 has been separated into 100 parts, and each part I'm checking how many values from this 100,000 values are present in each of those parts, and I'm basically plotting it on the y-axis. Okay, that is what a histogram essentially is. So we are just checking the histogram, and you will see that of the 100,000 values from 0 to 1, most of them are, in each of the bins the number of value is almost the same. So that's why this is from uniform distribution. As opposed to that, if you see the sampling from the x2 tensor, so there the content is not uniformly spread. So I have numbers all the way from about -4 to 4, and they are sampled in a normal manner, normal distribution, from a normal distribution. So you will see that the mean of this data is somewhere around 0, the variance is about 1, and I'm just checking within one standard deviation from in the data how many of the data points are lying within that region. So that is about 68%, which is what you would expect from a normal distribution. Okay. So this block is just for a custom print function, and you need not go through this. This is just I'm using it for the later part. Yes. The x2 tensor was sampled from a normal distribution, as I mentioned here. So rand n is for randomly sampling from normal distribution. And so this custom print function is just for visualizing the tensors in a much slightly neater manner, rather than let's say visualizing them like this. Okay, so that you will see in the next few blocks. We have a question, but if we sample very high number from random distribution, it should also become normal. No, it depends on the underlying distribution from which you are sampling. So in the first case we sampled from a uniform distribution. there also we sampled about 100,000 points. But since it was sampled from a uniform distribution, there is equal likelihood of each number coming. So we saw almost equal number of number of numbers in each bin. But in the second case, we have sampled from a normal distribution. So we got this. So we'll look at some operations on tensors. So here we have two tensors, x and y, which are random. So we are sampling them, the entries in, it's a 4x4 tensor, and we are sampling the entries in them from a normal distribution, as you can see here. And the tensors are printed in such a manner. And this print tensor function is what we have created here. So it makes it appear in a much neater manner. You will see that this is element-wise element-wise addition. So this number and this number, they are being added, and you are getting this number. Okay. So you can just verify based on what numbers you are getting. So about 0.3 and 0.3, some 0.6 number you are getting. So that should be okay. So this is an element-wise addition. So similarly, you can do subtraction, division, multiplication, whatever you want. Then we have slicing operations, which means in this case, let's say I want to take out from this x tensor, I want all rows and the first column, which means these entries. So minus 0.7294, 2. Just a minute, I will run this cell. Okay, so this first column, I hope my cursor is visible. So this first column, the column number 1 from x tensor, we are going to get it as this. So this is called a slicing operation, and you will often do such an operation with the data that you have. Then you also have resizing operations. So you have a tensor x, which is again, so it has a very huge number of dimensions. So 1, 4, 32 and 24. So it has 4 dimensions, and along each of them we have that many number of entries. So basically it has however you can imagine a 4-dimensional tensor object. So it has first row, 1 row, and then 4 columns, and the 4 columns have a 32-dimensional height, and whatever comes beyond that for the 24. So now we want to, let's say, resize this tensor into 5 dimensions of this size. So basically you can do this, and for if particular dimension you don't want to calculate by yourself and you just want to keep it, and you want the code to infer it on its own, you can specify this -1 as the dimension, and the code will figure out what is the size that should be along that dimension. Okay. So if we just run this, so the code has figured out, the library has figured out that along this third dimension also the entry should be 8. There should be 8 elements along that dimension. Okay. In very simple terms, it's actually just a product. So product of all these 4 numbers and product of these 5 numbers should be same. Then you will have the safe number of elements. Okay. Moving on, we can convert data from NumPy to Pytorch. So if you have an A which is a NumPy array, you can convert it from NumPy to Pytorch. Yes, if you want to reduce the dimensions also you can do that. So instead of this, if I maybe I'll remove these two dimensions. So from a 4 I am going for 3, and I will let the code figure out what is this dimension, and the code has figured out that the number of elements along that dimension have to be 192. So you can do something similar and test it out. Then as we are discussing here, so we can convert data from NumPy to Torch tensor, and as shown. So here we have a NumPy array with all entries 1. It can be converted into a tensor with all entries 1. You'll notice that by default it comes out to be float 64 float 64 entries. Next we have matrix multiplication operations. So we have just sent some dummy data in as mat1 and mat2, and we are taking a matrix multiplication of those. So if how is the calculation done? Maybe after the class you can include annotation for this. Calculation of what? Oh, I mean, I'm not doing that actually. It's being done by the library itself. It's basically, so 1 into 4 into 32 into 24. That will be the total number of elements in the X tensor. The library is just ensuring that the number of elements in this Y tensor, which is now a reshaped version of X, should be also the same. So it is just checking 1 into 4 into 32 into 24 divided by 8 into 2, and whatever is the remaining number, that is what you will see in this column. Can't we directly pass NumPy array into the tensor? Yes, you can. If you have a NumPy array, you can just convert it directly to a tensor. So matrix multiplication, as you can see, so this is a 2 cross 3 matrix, and this is a 3 cross 3 matrix. So resultant should also be 2 cross 3, and that is what you are seeing here. Next we have concatenation operations. So very commonly you will use two types of concatenations: the vertical stacking and horizontal stacking. So I have a tensor here, which is a 2 cross 3 dimensional tensor called A1, and another tensor 3 cross 3 called A2, and here I am going to concatenate them. So I am using a vstack function of Torch library, which is going to vertically stack them. So you can just see the output here. So if A1 is my tensor like this and A2 is a tensor, I am vertically stacking them one below the other, and you will see that the first 2 rows of A1, and it's followed by the next 3 rows of A2. Okay, so this is called a vertical stacking. Similarly, if I wanted to now do a horizontal stack, I can't stack A1 horizontally to A2 because number of dimensions, if I want to just take it and put it beside it, the number of dimensions are not matching. So I first need to, let's say, take the transpose of this. I can take the transpose of this. So transpose of A1 is now going to have dimensions 3 cross 2, and this transpose of A1 and the A2, I can horizontally stack them. So you will see that the first 2 columns are of this horizontal stacked matrix are the transpose of A1, and the next 3 columns are stacks, basically the of columns of A2. Okay. I hope this is clear. So these were some of the basic operations, and there are several more operations that you might come across, and you can find those from the Pytorch library. Just Google search and you will get them. I just want to quickly cover up this autograd functionality in Pytorch. So here, for the sake of this dummy problem, I'm considering a function y, which is a function of this variable x, and there are two parameters a and b. Okay, so the function is defined as follows: a times x square plus sine of bx. And what I'm doing is I'm generating about 100 samples of x. Okay, from they are right now equally spaced, so from -2 to 2 I'm just sampling 100 values of x, and I've just sampled the same amount of noise terms. What I'm going to do is now define a function which is basically this function: y is equal to ax square plus sine bx. Okay, and these are my original outputs, expected outputs. So my function, to which if I am passing my x values and this parameter values a and b, which I have defined here. Okay, if I pass that, I am getting the corresponding y values, and to that I am adding the noise, and that is making my y variable. So here I am just plotting it. So the data kind of looks like this. So the curve x square plus sine 5x, because my values of a and b that I have chosen are 1 and 5. Okay, so this is ax square plus sine bx. Okay, 1 and 5. Once I plotted that curve, that is what the blue curve is like. Okay, and the red dots are basically that curve with some noise added. Okay. So that is how the data is currently looking. So my goal now is to, for the sake of this question, I am going to assume that I don't know the actual values of this a and b. Okay, and I want to infer those from using Pytorch, basically gradient descent. Okay, the reason I'm doing this is because I want to show how the autograd functionality or the gradient descent implementation or optimization algorithms can be implemented in Pytorch. So just for the sake of it, I'm assuming that I don't know the actual values of a and b, and just using this red data points, I'm going to try to identify those values. Okay, so I'm considering AI and BI, some initial predictions of those two values a and b, and I'm sampling them as integers from up to 10, some random integers. Okay, now I'm defining two tensors actually, which are having the values of these which are initialized basically with these AI and BI, which are the initial values of A and B. Okay, but along with that, while creating this tensor, I am setting this parameter of the tensor requires grad as true. So doing this allows Pytorch to keep track of the gradients of so wherever this ag variable will be used anywhere in my code, Pytorch will basically keep track of the gradients of these two variables, and it will keep them, and whenever I want to evaluate loss with respect to these, I can do that. So that is why we have set this requires grad parameter as true, and I'm just printing this ag and bj down here. You will see, so randomly they were sampled. Right now they are 2 and 3. Okay. So this requires grad parameter value is true for them. Then I'm defining an optimizer, so which is an Adam optimizer with these initial values. So not initial values, rather these are the parameters. So I'm creating an optimizer, and I'm telling the optimizer that you should find the correct values for this AG and BG variables, and according to a certain loss function. And I'm just keeping the initial learning rate as 0.01. Maybe I will just write a slight comment here. Parameters. So these are two parameters which are to be optimized, and there is an initial learning rate value LR, which is 0.0. Okay. So I'm just setting the previous loss as some infinity number, and I have set an upper limit on the number of iterations as 100,000, but it won't take that many number of iterations. This is just for demo. So we are checking for iterations in this huge number. What we'll do is, at each iteration, we'll first try to compute the loss based on the current values of these AG and BG variables. So when we started, we randomly started with this 2 and 3 value, right? So based on this data, I'm trying to compute some loss. So what is my loss? So my loss is based on the data that I have sampled, which is this red dot that you can see. So x and y values are these red dots. Okay, that is what I'm passing to the compute loss function. Okay. What is in this compute loss function? I'm basically calculating a mean squared error between the prediction and the actual value. So I'm assuming here that the hypothesis function is actually already known for me. So this I'm doing so that you can see how, if you have a custom loss function, how you can use Pytorch. So in the reality, you won't be knowing the hypothesis function. This will come from your forward pass of your neural network, this part. But I'm here assuming that I already know what the hypothesis function is. So I'm putting here ax square plus sine bx, which was our actual function. Okay, but I'm assuming that a and b are not known. I'm just guessing those values. Okay, I hope till this point everything is clear. If not, just ask. Okay, so I have n number of data points. Okay, and I'm going to calculate the difference between the actual y value, which is what you will have along y-axis, and the predicted value from my hypothesis, which depends on the x value that is going as input, as well as these parameter values of a and b, which are these. Okay, so you will notice that the loss function is actually, since x and y are actually my already sampled, right? So these are my data points. So the loss function is actually a function of a and b. Okay, so when I take a gradient of this loss function, it will be computed with respect to a and b. Okay, so that is what I am doing here. I'm just taking a mean squared error of all of those values. Okay, just I will just run it. So this loss function is computed in each iteration first. Then I'm setting this optimizer.0 grad. So I don't want the previously computed gradients to be used for this iteration, so I'm just setting those as 0. then I'm doing loss dot backward. This is the step which actually updates the gradients. So right now whatever I evaluated the loss as and my parameter values were, so okay, so based on that, what is the derivative, what are the gradients in this particular iteration. So derivative of loss with respect to this AG parameter can be can be seen by this printing this AG dot graph, and that is what you will see here at the top. You will see the third print statement. This is the tensor. So this is the gradient of the loss function with respect to the AG parameter at initial tensor, the first tensor. When I do this optimizer dot step, this line, the loss will get updated based on our gradient descent law, so which will be something like, I'm just writing it for the AG parameter. So AG, let's say of iteration k plus 1 will be equal to AG at kth iteration minus some learning rate LR times this. So this is our classical gradient descent algorithm. Okay, so something similar to this is happening behind in this. Okay, and we are just printing for each iteration what is the loss and what are the parameter values A and B. Yeah, okay. I hope this part is clear. In case anything is unclear, please ask. And we are just checking also that whether our loss is within, so previous loss and the current loss, if it is less than 1e minus it, we will stop the process and the code will stop. We don't need to run for all these 100,000 records. Okay, so a typical iteration would look, let's say, something like this. So we are printing the loss in that iteration and the parameter values at that point. So we started with 2 and 3, and over iterations the values of A and B are changing. So right now it's close to 1 and 3, 2 and 3. Over time it will change. At the end it is going from close to 1 and 5, which is what our real data, when we created the data set, that is what the values we had set. Okay, the model has basically identified those. But what I actually wanted to show from this demo is how you can implement a custom loss function, and this kind of thing will be useful if you are working on something like PINs, physics informed neural networks, where your loss function will be based on the physics. So in such an operation we might need to define our own custom loss function, and this is how you can do it. Okay, that's it. So that completes the Pytorch basics demo, and you can try it out on your own, experiment with this code, and feel free to ask any doubts. We'll take a short break and then we'll move on to the next step. the next demo will start at around 7. If you have any doubts, feel free. Okay. Then we'll move on to the next demo. Yeah, Adam optimizer is just a random choice. There are many actually optimization algorithms present in these frameworks. So there are, in fact, that itself is a separate area of research. Generating a correct, good optimization algorithm. So there are the classic gradient descent and some momentum-based optimizers. Then the Newton methods, then quasi-Newton methods. One of the example will be the LBFGS optimizer for quasi-Newton method. Then there are RMS prop, there is ADA grad, ADA boost, all its variants. Yeah, I mean there are lots of optimization algorithms, but just for demo we have chosen. Can someone check if this link is available? Okay. So I hope this you are able to access this colab notebook. You can do the same what you did for the previous one. You can create a copy of this notebook in your local, in your Google Drive, and you can test the code again. So this time I will try to connect to colab. So I'm not able to actually connect to GPU today because I have already exhausted my free usage capacity. in case you are also not able to do that, maybe you can go to this runtime and click on manage runtime. For you, the previous code might be showing here the GPU execution, and you can just delete that runtime and you can start again for this. If possible, try to connect it to the T4 GPU. If not, that is also fine. The code will see. Whenever it gives you the option, you can try it again. Okay. So in this demo, maybe I'll first, before jumping to the demo, I will first give a brief summary of what the demo is about. So in this demo, actually, I'm doing a task called image denoising. And this is being particularly done using convolutional autoencoder. There are traditional ways to do it also, but just for the sake of this demo, we are going with going to do it with convolutional autoencoder. The idea is that on this, your data set have some number from the MS data set, let's say 5, and there will be some noise added on top of this. It will make it difficult for us to identify what this number actually is. Okay, and you will train a network which will correctly remove the noise and give you back the number behind it. Okay, so that is what a convolutional autoencoder is. All I'm going to allow you to do in this demo. Okay, so basically there will be a series of convolution layers. Followed by a series of transpose convolution layers. Fine. So this image that you have, you will basically apply filters on top of it, make it smaller and smaller, and then you will reduce its dimension to a certain smaller number. At this point, it will only carry the information about the number itself, and the idea is that throughout the process of these convolution layers, the information about only the number is retained and the noise is removed. And once the information about the number is present, but this is now present in a smaller dimension and it's not present as an image, so you will now use a transpose convolution layers to upscale it, and you will get back the original image. So that is what we are going to see. Okay, and in this example, we'll see how to create a convolution network. We will see how data loaders can be used in Pytorch. So data loaders is a very important concept. The idea is that you don't want to load the entire batch or the entirety of your data set, which can sometimes even be in orders of GBs. You don't want to load all of it into a GPU memory for simple reason that GPU memory is actually limited. So in such a scenario, you can opt for data loaders, which will pass in a certain amount of data, like say a batch of data. It can pass and transfer it to the GPU memory. Then it will evaluate your forward pass through the model, compute the loss, and compute the gradients, all of that. So the data loaders is actually a functionality which allows you to pass parts of the data rather than the entire. You will see that here. Then you will also look at the profiler and the Tensorboard and how you can use those in colab for your code. Okay. So that is the summary of this demo. If you have any doubts, you can just ask me. So I'll jump to the demo. So to start the demo, you will see that there is this command, and exclamation here mark here actually allows the notebook to run the command line instructions basically. So for this we need to actually update the Tensorboard which is already present in the colab service, and we have to install this library called Torch Tensorboard profiler, which will allow you to visualize the profiler also. So the purpose of a profiler, as you must have seen in the content of the course, is that it will allow you to check what part of your code is basically consuming how much of the computation resources and so on. Okay. And if your code is very complex, then that analysis might help you make it more optimal. So here we are just calling a bunch of libraries. You will see this torch.nn model, which is the most important part here. So this torch.nn model basically has a lot of layers which are already defined. So when you want to, let's say, create a simple neural network, you will have a functionality for that. If you want to create complex layers such as convolutions or LSTM operations, all of those, so those can also be directly called, and so all of these are related to the forward pass of the neural networks. So all of those are available in this torch.nn model. Torch.optim, as we saw in the previous example also, this is having the optimizers. There is another module called Torch Vision, which basically has some commonly used data sets which are available for us to try out some simple codes along with their predefined data loaders. So we will make use of that. Then torch.utils.data here is going to allow us to use this data loader functionality which I described, matplotlib, numpy, and Tensorboard. So to visualize your training process in a live manner rather than looking at the numbers themselves, you can visualize the training process in with the plots. So Tensorboard will allow you to do that, and your torch profile, which I just described. Okay. Then we'll look at the definition of our neural network, which is a simplified architecture of a unit, but this is not like the real unit, but this is a much simplified version. So we have two parts of the network. One is the encoder part and the decoder part. Okay. The encoder part is basically a bunch of convolution layers, and the decoder part is a set of transpose convolutions. So all of these definitions are coming from this torch.nn model. Okay. And we don't specifically have to do that. They are available. So as you can see here, I will just go through these two to give a summary of it. So basically, when you want to put a bunch of layers one after the other, you can use this nn.sequential functionality. And what you are doing here is, first you have a convolution, 2D convolution layer. Okay. To this, your image goes as the input, and this 64 here is telling the number of output, the dimension of the output kernels, the number of filters basically, and in a convolution network. 3 is the size of the kernels, and you are applying a padding of 1. Okay. And this process will basically shrink down the size of the image. So you will be starting out with I think if I'm not it's around 128 cross 128 image of a digit, and finally you will have a 14 cross 14 image, but with 64 filters. Okay. So you are applying these layers, convolution layer, then the activation function ReLU, and then a max pooling layer, all of these, and at the end of it you are getting a reduced dimension representation of that image, but in 64 of such filters. And you do the exact reverse process to get back the size, and at the end you will have a transpose convolution layer. And this will, at the end of this, you will have basically recreated the image size same as the image size. And the forward pass of your function will look like x, which is the noisy image that goes as input, and x1, which is the reduced dimensional representation, and from that you are decoding and obtaining back the image. Okay. Here are some basic utility functions for defining the noise. So we are adding a salt and pepper noise to the image. You will see how that looks like in a bit. We are converting all our data to tensors. That's why this transform.toTensor online is present. And we have here the data loaders idea. So as I said, you don't want to load the entirety of your data set at once. So instead you are loading 32 images at a time. So the batch size of 32 is denoting that. Okay. And we are using this MNIST dataset from Torch Vision module. So that is what our training dataset is. Then we are defining the model, which is this model that we defined here. Okay. A detailed why this U super class and all of this, that is described in the lectures. So I won't go through them again. You can look at this code again, and if you have any doubts, you can ask. Then we are defining our loss function, which is the mean squared error between the original image and the predicted image. Okay. And our optimizer again Adam with initial learning of 0.03. This is our Tensorboard writer, so writer object, which is going to be used to, let's say, plot the loss over the epochs, as well as it is going to it will also plot how the images are looking over the epochs, how our model is doing over the epochs. That also we'll see how that is done. Then we are checking if we have device GPU or not, and if it is available, we'll send it to GPU. So right now I'm not running it on GPU, it's running on CPU only, since I'm not able to access it. But if you are able to access it, you can use it. Okay. So this is a summary of our unit model. So I will just run this cell, and it should download the MNIST dataset basically from the server. It will take some time. Okay, it is done. So next, you can just load the Tensorboard using this command. And you will not see any output right now for any of these, because these two files, run unit MNIST experiment and run profiler, right now they are not created. There is nothing in this folder. Okay, so they will come up when as you run the main command. So this is our main training loop. We are setting up the profiler here. Okay, so what this profiler is going to do is, it's going to look at the it's basically covering up how your entire training loop, and it's going to give you some inferences based on this. Okay. So I'll go over this later. There are some basic arguments that you can provide for the profiler. The main idea is your training loop, which is right now we are running it for 50 epochs, and for each epoch what we are doing is you basically take your data from the train loader, which is your actual image of a digit, then you add some noise on top of it, and then you send this image or basically the noisy input to the GPU memory. You don't need to do this actually, but you can send the noisy image to GPU memory. Oh, actually you need to do this as well. So you need to take a difference of that. So this noisy image is now going to be passed to your model, and the model is going to create a denoised image. Okay, and you are computing the loss between the output and the input based on your loss function, which is in this case mean squared error. Then you are updating your gradients, and you are optimizing the weights of the function network. And here we are doing the profiler step also, so that it can also update it. And then we are computing our current running loss, and we are writing that to our Tensorboard, okay, for visualization. And similarly we are evaluating, so out of the 32 images that are going in each batch, we are going to take 8 of those, okay, and we are going to show you what the actual image is like, how the noisy image looks like, and how the predicted image from your model that looks like. Okay, and then we are going to plot all of that in using Tensorboard. Okay, so I'll just run this function also. Once the training process will start, you can go over here and reload this. After some time, I think that should have. It will take a little while since this is running on a CPU. Yeah, we'll come to the what profiling is actually doing. We'll just see how this thing looks like this. Oh, maybe I have a printing typo here. Just remove this backslash in front of the runs. I need to restart this. Once you have done that, just restart, do this disconnect and delete runtime, and just restart and run off. I mistakenly put that backslash here. It is not actually present. Once the visualization loads, we will get to see what profiling is actually doing. You can just click on this gear here and click on reload data, so that every 30 seconds the model will update what the current progress is. So we are now able to see the profiler as well as the run summary. Okay. Just give it a minute and we'll also be able to see the images in the way. Yeah, so this model performance tab, yeah, here you can see basically how the data was like. So your original data is having a bunch of numbers, the images of these numbers, which is completely free of noise and they are clearly visible. The noise that we additionally added is making it extremely difficult to discern what the underlying number is, but the network is now trying to understand what was the number written below it, and you'll see that over epochs it is slightly able to do that job. Okay, so if you keep it for running, every 30 seconds it will update the image here, and we'll also be able to see the loss over the epochs, okay, in this bottom plot. You'll see that now even for us, in general it's very difficult to identify the number, let's say 7, which is written below this, but with generalization the model is able to understand that. and you will see that the loss is decreasing over the epochs. This number here down is actually the batch number, because that is what we are putting in the code here. Okay. So that is what this visualization kind of things you can get done with Tensorboard. Okay. And now the model is slightly better, I think. But if you keep it running, I think about in few hundred epochs, not few hundred epochs, I think we are running for 50 epochs. Yeah. In about 10 epochs, you should see a really good performance. We'll now just look what all the profiler has told us. So on an overview, since our code is completely CPU executed, it's telling that 94% of the computation is happening on CPU, which is not a surprise. In case we are using GPU, maybe it would have shown another column for GPU. If you are doing it, you might be having it an entry for GPU as well. Is anyone having it? Okay. Yeah. If you are running through a GPU available system, you might be able to see that. Here most of this is general stuff, but you can look at more specific stuff also. So you can look at what is the amount, in terms of time, how much each operation is taking. So you will see here that the convolution, basically the gradient computation of these convolution layers, that is taking most amount of time. Okay, so that is what is shown here. And this is probably for the forward pass. Maybe it's the same thing. Okay, so there are a bunch of processes. Let's say max pooling layers, the convolution layers, in max pooling, thresholding. We have the mean squared error computation, copying of the data, and so on. There are several processes that are happening in your code. You can visualize on a pie chart here which of the processes is taking the most amount of time, and depending on the complexity of your code, this information might help you write some of the parts of the code better. That's the idea. You can analyze here for each of them whether tensor cores are available for such an operation. So for computation of convolution layer, tensor cores are eligible, but right now we are not using any because this is a CPU system. Similarly, you can look at let's say memory usage. So over time, what is the memory usage of your system? So that you can check. Then which module it's computing, basically taking how much time. So loss computation is not taking that, is taking a lot of time in fact. And the unit, the model that we created, that is also taking some time. Okay. And let's see. Okay. So that is the overall summary of how you can use or run profilers in the code that you are working with. We'll just check how our results are looking. So looks like our results are much better. So even with this noisy image as input, the model is able to predict that there is 6 underneath this. And over the batches, how the loss is reduced. You can have separate tabs for scalars and images. So in case anyone has any doubts about these demos, feel free to ask. If anyone has any doubts about the demo, feel free to ask. You can try and run this on your own also. You can try modifying the codes, try some different experiments with it. By show of hands, can I know how many of you were able to run the codes along with while I was showing? Hello? Nobody was able to do? If there were any issues, you can let me know. We can try to correct some of those issues. Hello? we have about some 10 minutes. We can cover some doubts if you have. Oh, sure, sure. If you have any doubt that you have right now, you can also ask me. There is no problem. I mean, what part of the demo did you feel complicated? The convolution autoencoder part is not something that I'm expecting uh, like to cover right now. Actually, there is a previous course that I did as a PhD for another previous course called Machine Learning for Engineering and Science Applications, NPTEL course. There I, based for that course content, I showed this demo. There I described in much detail about the autoencoder as well as the working of a convolution neural network. And you can in fact look at the lecture videos of that course as well to better understand the architecture. The more important part here was actually to just see how the implementation of these networks can be done through Pytorch, and just basically to get familiarity to these tools. Yes, that is what you should. There was a typo, that slash was not supposed to be there in front of runs. The Tensorboard is not loading. Maybe you can just instead of try to go to runtime, disconnect and delete the runtime, and start running it from start by clicking on this run on. It will load after some time. The Tensorboard won't load immediately because you are starting the Tensorboard and then the data for it is being generated here in the training week. Okay, you can try it out. Is anyone else having similar problems? Are you able to run the code or any errors or unexpected? Now, in case if nobody is having any doubts, we'll wrap up the session. If you have doubts, feel free to ask. You can feel free to post any doubts if you have in the discussion for now, or related to what content I am showing. If you have any doubts, you can send me an email at this. Okay, good. So are you able to run it on a GPU runtime? You can check at the top whether your runtime is GPU. Here, if T4 is written over here. It's a GPU runtime. Okay, good. If possible, you can share your screen, and we'll see this profiler for your case. In the overview, we should be seeing a different pie chart for your case. I will stop sharing my screen. You can share yours. Scroll below. Yeah, in the profiler, yeah, this is the overview. Good. So you should be seeing that the details about GPU utilization and all these details. So the CPU is taking far less, and in this case the GPU is using more computation. Okay. So we can see a breakdown of all these parts of the code. There is a performance recommendation. Can you scroll down? Yeah, so GPU 0 has low utilization. You could try to increase batch size to improve. So this is what profiler is recommending us. So in fact, if you click on that, beside the T4, there will be two graphs are there at the top, RAM and disk. You don't need to click on it, just hover over it. Hover over the graphs, and you will see at the top that the RAM that is available in that system. This is actually the CPU RAM. If you run the NVIDIA SMI command, you might see the GPU RAM. If I remember correctly, it was around 15 GBs. So in this case, what the profiler is recommending us is to increase the batch size so that we can pass more data. Since it's 15 GBs, you can pass in almost the entirety of the data and run the model, and it will train much faster. Okay, so good. We are able to see that. Maybe you can check other views also beside the overview. So maybe GPU kernel. Yeah, so we can see this is a good example. So we can see whether our code is actually using Tensorboard or not. So right now it's not using any Tensorboard. If you scroll below, maybe not in this one, maybe the other one, in the operator. Yeah, if here we can see which of the operations can actually utilize Tensorboard. So the two main operations which can utilize Tensorboard in our case are the convolution. You will see CUD and convolution, but right now we are not using that. So we'll see that later, how that can also be done. Okay. But this code is utilizing GPU memory. That is what we will see. So you can see the memory on GPU as well as on CPU. If you click on CPU, I think it should have much lesser peaks. Yeah, the value is around 0.3 MBs, whereas for CPUs it was around 49 MB. Since the code is heavily relying on GPU. We were able to show the required content of the networks. Okay, so you can stop sharing the screen, and we are almost to the end of the session time. So we'll wrap up the session. If anyone has any last comments or something, we can. If nothing is there, we can close the session. We'll wait for a few minutes. Thank you for attending. Thank you for attending the session.